This is Higher Physics Notes, Unit 1, Section 2, Forces. This is the final note, Part 7, the body on a slope problem. Right. Let's begin with the situation diagram that we're talking about. So the sort of situations we're dealing with here involve a body that's on a sloping road or runway of some sort, something like this. It could be a car going up a hill, for example. Quite a common scenario. There we go. Move that up a wee touch. And if you're ever drawing this slope, just draw a triangle like that. It's the easiest way of doing it. There we are. Now we define the slope angle to be theta. Okay. The object will typically be a car, could be a car pulling a caravan, that kind of thing, and it could be powering itself up the slope if it's using its engine force, or it could be rolling down the slope purely under a gravity. It just depends on the situation. But what we're going to do is draw a simplified diagram here of the situation. So I'm going to take the body and just draw it as a dot. This is to keep my diagram simple. Okay. Now, let's just use those. So that's my body, could be a car, whatever it is, okay. And I'm going to draw my axes perpendicular to the slope and parallel to the slope. Well, the slope already gives me that axis, so I don't need to worry about it, okay. Now, why am I drawing my axes like that? Because any motion that the body undergoes is either going to be down the slope or up the slope. So it makes sense to make my x direction the parallel to the slope and my y direction at right angles to the slope. So let me just put in my x-axis now then. There you can see it. So there basically is my y-axis, and there is my x-axis. Right, let's get the forces on this body. The body will have mass m. Well, obviously weight acts, you can't escape that. And that makes a right angle with the horizontal. Okay. Notice that there is also a right angle between that y-axis and the x-axis, as one would expect. Right, so that's basically our weight force mg pointing down there. And what we're going to do is simply resolve this weight force into its two perpendicular components. One component along the y-axis and one along the x-axis. So let's draw in these two components. So here's the one along the y-axis. Don't know what happened there. And I need to do that one again. So here's the component along the y-axis. So that would be basically mg Now we've got to decide whether it's not mg itself, it's going to be a component of mg. So we need to work out whether it's a sine theta or a cos theta, but we'll do that in a minute. We'll just call it for the moment mg with a space waiting for the cos or the sine theta. Up here we're going to have our x component down the slope, and that's going to be mg something as well. So we need to get the sine and the cos thetas in there, because obviously these two blue vectors are not just mg on their own. Well, here's what we're going to do. So if you look at the triangle with theta on the left, and then the vertical mg line going up, what I'm going to do is I'm going to call this angle in here alpha. Okay, and I hope you would agree that theta plus 90 degrees, that's the right angle in black down at the bottom of the mg vector, plus alpha all add up to 180 degrees. In other words, theta plus alpha must be 90 degrees. Have a look at that. Theta plus alpha gives you 90 degrees. Okay, so far so good. Here's the question. What's this angle in here? Well, if you look at that angle, it is part of a right angle with alpha. If you look at it, along with alpha, it makes up that upper right angle. So basically this angle, whatever it is, plus alpha gives you 90 degrees. But hang on, the angle that when you add it to alpha gives you 90 degrees is theta. So that must be theta in there. Now, as soon as we know that, we can immediately say that the component perpendicular to the slope is mg cos theta, and the component parallel to the slope is mg sine theta. You can go away and work on that and redraw it if you want to try and work it out yourself, but that I can assure you is the case. And in case you're wondering if mg cos theta is the only component in that direction, why is that object not moving down in the mg cos theta direction? That's because the slope itself has a normal reaction force, we'll call it r, and r and mg cos theta balance each other, so there's no movement in the y direction, so we tend not to worry about that. But if you look at the x direction, that's the parallel to the slope direction, we've got mg sine theta down the slope. Okay, so that really is the key bit of learning here. The component of weight down the slope always equals mg sine theta, where m is the mass of the body, of course, in kilograms. G is the gravitational field strength, 9.8 newtons per kilogram, and theta is the slope angle as defined above. So whenever you have a slope situation, slope angle theta, you know that the component of weight down that slope will always be mg sine theta. Important note, understand derivation no need So you don't need to memorize this derivation. You won't be asked to do that. But what you do need to memorize is the equation and what it means. So you need to know that whenever you get a body on a slope, that the component of the weight down that slope will be mg sine theta. Just before leaving this scenario, it's quite common for there to be frictional force. Friction, of course, always opposes the motion. So if this body were to be going down the slope, there would be a frictional force opposing the motion. Be careful though, because if it's a powered vehicle and it's actually going up the slope, then the friction, of course, would oppose that and be going down the slope. So you have to just be aware of these different scenarios as you meet them in doing problems. So that's the body on a slope situation.